And welcome to another pre-calculus video. This one we're going to begin section 2.7, non-linear inequalities. 3 bullet points: solve polynomial inequalities, and then we'll look at rational inequalities. I think that'll be in the next video, and then use non-linear inequalities to model and solve real-life problems. Okay, first, sort of a little warm-up here. True or false, x is less than or equal to 7. So if I gave you, like for A, let's say x is equal to 8, is that statement true or false? Is 8 less than or equal to 7? No, that would be false. What if I said x equals 3? Is 3 less than or equal to 7? Well, that would be true. So here, these would be a linear inequality because that is x to the first power. But if we have x squared or x cubes, they're going to be nonlinear inequality, but we'll still be able to determine if that statement is true or false for different x values. So let's dive in with first I guess we got to read this. To solve a polynomial inequality such as x squared minus 2x minus 3 is less than 0, we'd use the fact that a polynomial can only change sign from positive to negative or vice versa at its zeros, the x values that make the polynomial equal to 0. Between any two corresponding consecutive zeros, polynomials must be entirely positive or entirely negative. That would be until they get to the next x-intercept. This means that when the real zeros of a polynomial are put on in order, they divide the real number line into intervals in which the polynomial has no sign changes. These zeros, we call those the key numbers of the inequality, and the resulting open intervals are test intervals for that inequality. For example, x squared minus 2x minus 3 would factor down to an x plus 1 and an x minus 3 factor. So if we set each of those equal to 0, we're going to get x is negative 1, and we'll get x is positive 3. So those would be points on our number line. Here's negative 1 as an x-intercept. Here's positive 3 as an x-intercept. So that gives us this interval of negative infinity to negative 1. We'll test that interval to see if it's true or false. We've got another interval from negative 1 to 3. We'll pick a number in there and test it. And our last interval will go from 3 to infinity. So here we found two key numbers that chopped our number line up into 3 intervals. So to solve this inequality being less than 0, we need to test only one value from each of those intervals. When a value from a test interval satisfies the original inequality, we can conclude that the entire interval is a solution to that inequality. Okay, so now let's try one. Oh, I guess we got to read more. To determine the intervals on which a polynomial are entirely negative or entirely positive, use these steps. First, find all the real zeros of the polynomial and arrange them in increasing order. These are called the key numbers. Use the key numbers to determine the test intervals. Step 3, we're going to pick one representative number from each test interval and evaluate the polynomial at that value. When the value of the polynomial is negative, the polynomial has a negative values for all the x's in that entire interval. When the value of the polynomial is positive for the test value, that polynomial has positive values for all x's in that test value. Because think about it, if this is the x-axis and I've got two x-intercepts, if my function goes underneath, it's not going to get back above the x-axis until we get to another x-intercept. So for that entire interval, every x value gave us a negative result. Okay, do we finally get to do one? Yes, here we go. Example 1, x squared minus x minus 6 is less than 0, and then they want us to graph the solution set. So let's sort of do the graphing as we go. I'm going to just draw a number line. It's supposed to be a straight line, but good enough. Okay, let's find the zeros here. So, this is less than 0, but to find the zeros, let's just say that is equal to 0, and then we're going to factor it. What factors multiply to negative 6 and add up to negative 1? Well, that's going to be an x minus 3 and an x plus 2. Plus 2. Remember, this is equal to 0 because we're finding the zeros. Now, if I set my first factor equal to 0, x minus 3 equals 0, we know that x is positive 3. And for our other factor, if we set x plus 2 equal to 0, we get x is negative 2. This is what the book is now calling the key numbers. The key numbers chop up the whole real number line into intervals. So our lowest key number is negative 2. I'm going to put that right here. And then we've got positive 3, positive 3. Okay, now I'm going to keep my factored form there. Okay. So what we can do here, first we're going to list our intervals. I'll just abbreviate it intervals. Always the farthest on the left is negative infinity, and we'll go to our lowest key number, that would be negative 2. So there's our first interval. The next interval picks up where the last one left off at negative 2, and this one will go to the next key number at 3. Now we're out of those key numbers, so our last interval will go from 3 all the way to infinity. So we've got our intervals. We are going to pick a test number or a test value from each interval, and then we're going to put it in here to see if our answer comes out to be positive or negative. So I'll write here positive, negative, question mark, and then we will come up with our conclusion. And actually, I'm going to move my number line up here and get that out of the way. Okay, so let's see, our first interval, negative 2 to negative infinity. I like to work with negative 10. It's easy to multiply and divide by 10 because you're just moving decimal points. So now here we got to figure out if our polynomial is positive or negative. Notice here we factored it into two factors that are multiplied together. I'm just going to plug my negative 10 in here, and my first factor will be negative 10 minus 3. That's negative. And if I put my negative 10 in for this x, I'll get negative 10 plus 2. That's also negative. Notice I don't care what the value is, just the sign. So here, negative times negative is positive. And now for the conclusion. I got rid of the original inequality. If I bring that back out here, remember we were looking for less than 0. So I'm going to go here, make this equal sign into a less than. So our conclusion is positive. Are positive numbers less than 0? Well, that would be false. False. So we're not going to color in that part of our number line. This interval from negative infinity to negative 2 will not be colored in. Let's go to our middle interval here, negative 2 to 3. If it's available, the greatest number to use is 0. So our test value is 0. So here, 0 minus 3 would be a negative 3. And then here's 0 plus 2 is a positive 2. So what we've got is a negative times a positive. Well, that's equal to a negative. And are negative numbers less than 0? Yes, they are. So that's going to be true. And we can color in the interval from negative 2 to 3. So I'm going to go up to my number line here from negative 2 to 3. That would be colored in. That is a true part of the graph. Last interval, 3 to infinity. Great number to use, positive 10. If I put the positive 10 in here, 10 minus 3 is positive. And if I put the 10 in here, 10 plus 2 is positive. Positive. A positive times a positive is a positive result. And remember, our conclusion, we're looking for less than 0. Well, positive numbers are not less than 0, so that's also going to be false. So there's our solution set. All the numbers between negative 2 and positive 3 will make the original inequality a true statement. And something else to point out here, we're going to see this a little bit later. Let me bring this down here. Okay. This x squared minus x minus 6, its general shape, x squared is a parabola. It's positive x squared, so it opens up. So here the number line is the x-axis, but if I drew the y-axis in there, I would have a parabola opening up. And we know the x-intercepts were negative 2 and 3. Remember, our inequality was less than 0, so the true part is where our parabola was under the x-axis. And what do we got here? Yeah, there's the book graph of that. Here's their number line from negative 2 to 3. Those are the true part of our number line for the given inequality. And then if I just drew the parabola like this, there's the second graph. You know, we went through the x-axis. And there's our y-axis. The part of the graph that was true was under the x-axis due to the less than 0. Okay. A little trickier one. 4x squared minus 5x is greater than 6. You know, the last one we had it was a 0 there. So probably the first thing we're going to do here is move that 6 over and make it a negative 6. 4x squared minus 5x minus 6. And you know, this is a greater than sign, but we're going to find the zeros. So let's set it equal to 0 and see if we can come up with the factors. Okay, 4x squared has to be a 4x and an x or a 2x and an x. We're going to go with 4x and x. And then to get the minus 6, we're going to use a minus 2 and a plus 3. X minus 2, 4x plus 3. Let me check my outers. My outers would be a minus 8x and a plus 3x. That does give me the minus 5x in the middle. So there's our factorization. And if we set each of those equal to 0, 4x plus 3 equal to 0, we would first subtract 3. 4x is negative 3, and then divide by 4. X is negative 3/4. There's one of our key numbers, and the next one, x minus 2 equal to 0, means x equals 2. And I'm going to keep my factored form there. That's the one I like to evaluate with. And we'll get this other stuff out of the way. And I guess I can put back in my inequality that's greater than. And we had a 0 over there after we moved the other stuff to the other side. Okay. And I'll start sneaking my graphical up here. So here's our number line. And we've got, I'm going to use red ink. Here's negative 3/4, negative 3/4, and positive 2 are our key numbers. So those are going to chop up our intervals. So our intervals are going to be negative infinity to negative 3/4. And then the next interval picks up at negative 3/4 and goes to positive 2. And then finally we'll go from 2 to infinity, since that was our last key number. So there's our intervals. We are going to pick a test value. Again, I really like to use negative 10. And the middle one we can use 0. It'll fit in there. And then 2 to infinity, let's use 10. Okay, so we got to find the sign of our inequality. And if I underline it here in red, we've got one factor times another factor. So for each of these, we're just going to figure out what we're multiplying together. All right, first up, negative 10. If I put a negative 10 in for this x, I'll get negative 40 plus 3. That's a negative number. And if I put the negative 10 in for this x, negative 10 minus 2 is also negative. A negative times a negative is positive. And in this case, we are looking for numbers greater than 0. So are positive numbers greater than 0? That would be true. That would be our conclusion. So if we wanted to right now, we could color in the negative 3/4 to negative 8. And since it's strictly greater than, we would use a parenthesis. And we're going to color in that part of the graph. All right, let's go to 0. If I put 0 in for the x in this term, 4 times 0 is 0, and then plus 3 is positive. And if I put the 0 in for this x, 0 minus 2 is negative. A positive times a negative is negative. Are negative numbers greater than 0? Of course not. So that's going to be false. False. We will not color in the interval from negative 3/4 to 2. Last up, 2 to infinity, we plug in a 10. 4 times 10 is 40. Plus 3 is a positive number. Put a 10 in here. 10 minus 2 is 8, positive 8. Positive times positive is positive. And positive numbers are greater than 0. So that is also going to be true. So we'll color in, parenthesis here at 2, and we head off to the right. Now, you might fall into the pattern of you're going to have a true and then a false and then a true. It's going to alternate. Remember, sometimes you can bounce off the x-axis. You can touch and turn. So it is quite possible to have 2 trues in a row, or even 2 falses in a row, depending on the inequality. and if you bounce or cross at that x-intercept. So here's our graphical solution on a number line. And what we could do is also, remember this is going to be a parabola. If I bring down my original problem, it's a positive 4x squared, so this is a parabola opening up. And remember, in this case, our inequality was greater than 0. So if I did draw my two-dimensional parabola opening up, the true parts are where we're above the x-axis, so we colored in here. Here we're above the x-axis, so we're coloring in that interval. Notice, since we're greater than 0, we would not color in the part that's underneath the x-axis. And here's their graphical. Yeah, if we could even graph that on a TI-89, and we could figure out the intercepts and then figure out which way the parabola opens and what our solution set would be. Here's a couple for you to try on your own, very similar to the ones we just did. So find your zeros, figure out your intervals, and test them and see if you got it right. Of course, pause the video, no cheating. Do it on your own. Okay, first up, let's factor. X minus 5, x plus 4. They add to the negative 1, multiply to the negative 20. And if we set each to 0, you're going to get x is 5 and x is negative 4. So there's our number line, negative 4, positive 5. Okay, first interval, negative infinity to negative 4. Let's test negative 10. I'm going to put negative 10 in here. Negative 10 minus 5 is negative. Negative 10 plus 4 is also negative. Negative times negative is positive. And our inequality in this one is less than. So our positive numbers less than 0? No, they're not. That's false. We're not going to color in that interval. Next up, negative 4 to 5. We can use good old 0. 0 minus 5 is negative. 0 plus 4 is positive. A negative times a positive is negative, and are negative numbers less than 0? You betcha, true. So we can color in that interval from negative 4 to 5. Again, it's a strictly less than inequality, so we would use parenthesis, no brackets, and color in between. Last interval, 5 to infinity. Use good old positive 10. 10 minus 5 is positive. 10 plus 4 is positive. A positive times a positive is positive. And positive numbers are not less than 0. So that's going to be false. We will not color in that last interval. Okay, the juicier one. First, move over the 5 by subtraction. 2x squared plus 3x minus 5 is less than 0. And let's see, our factors are going to be a 2x plus 5 and an x minus 1. And if we set those equal to 0, let's see, we're going to subtract 5 and then divide by 2. And here we're going to add 1. So there's our key numbers for our number line. I'll do a little number line up here. So we've got negative 5 halves, that's about 2.5, and we've got positive 1. I'm going to keep my factored form. So we're going to do intervals. We're going to test a number. We're going to find our sign, positive or negative, and in this case, again, we're just going to be multiplying two terms together. And then we're going to come up with our conclusion, true or false. First interval, negative infinity to the negative 5 halves. Again, that's 2.5. So negative 10 is a great one to use. Negative 10 times 2 is negative 20, and you add 5 more, and it's still negative. And then here, negative 10 minus 1 is also negative. Two negatives multiply to a positive, and our inequality is less than 0. Are positive numbers less than 0? No, they are not. That is false. Don't color in that part of the number line. Next interval, negative 5 halves to positive 1. 0 is right in there, so let's use 0. 2 times 0 plus 5, well, that's positive. 0 minus 1, well, that's negative. Positive times negative is negative. Are negative numbers less than 0? Yes, they are. True. So that interval in the middle is going to be colored in. Again, since it's strictly less than, we will use parenthesis, color in between. Last up, positive 1 to infinity. 10 is a great number to use. 2 times 10 is 20, plus 5 is positive. 10 minus 1 is positive. Positive times positive is positive. And are positive numbers less than 0? No, they are not. False. So there's our graphical solution. All numbers between negative 2.5 and 1 will make the inequality true. Any other number will make it false. Okay, we got one more example, one more huddle, and wrap up this video. Example 3, ooh, it's got a cube in it. It's got 4 terms. Holy cow. Don't worry, we're going to move that 48 over by addition, and it looks like we'll just factor by groups. 2x cubed minus 3x squared minus 32x plus 48 greater than, well, let's set this equal to 0 because we're finding our zeros, but our original inequality is greater than. First, pull out an x squared, leaving a 2x minus 3. If it's going to work here, we're going to factor out a negative number, so that'll make this a minus, and we need a 2x minus 3 in here. What would we factor out? Well, 16. 16 times 2 is 32, so there's our 2x. 16 times 3 is 48, there's our 3. So here we've got an x squared minus 16 factor, and we've got a 2x minus 3 factor. Let's factor the x squared minus 16. We could set it equal to 0, but we could also factor it into an x plus and minus 4. And then we've got 2x minus 3 equal to 0. Okay, so here, if we set this one equal to 0, we'll get x is 4. And the one in the middle, we'll get x is a negative 4. And for the last one, to get x alone first, we're going to add 3 and then divide by the 2. So in this case, we have 3 key numbers, which means we'll have 4 intervals. And let's see, I'm going to stay right here. Well, actually, when it comes to evaluating, why, there we go. When it comes to evaluating, we can evaluate either in the this factored form. We can plug our test values in here and see what happens, or we could put it in the 3-termer. It doesn't really matter. Let's stick with the 3 terms. What the heck? And I did back. There's a 4 there. Or no, that was 3 halves. Get back. Add 3, divide by 2. So there's our factored polynomial. And our inequality in this one is greater than. I'm going to put that back in before I forget. So this is greater than. Okay, intervals. We always start at negative infinity, and we're going to go to the smallest key number, negative 4. The next interval will pick up at negative 4 and go to the 3 halves, or 1.5 if you don't like fractions. And then we're going to go from the 3 halves to the positive 4. And then finally, we're going to go from 4 to infinity. So there's our 4 intervals. Let's find test values for each. So the first one right in there is the negative 10. That'll work nice. From negative 4 to positive 3 halves, 0's in there, so that'll be a good one. The very last interval, we can use good old faithful 10. But here's one between 1.5 and 4. We can pick 2 or 3. What did I pick? 2. I used 2 when I did this in my notes. So let's come up with our sign. Now in this case we have 3 things we're multiplying, 1, 2, 3, to figure out if our overall answer is going to be positive or negative. So 3 things multiplied. First we're putting in a negative 10, so that's going to be negative here. Negative 10 plus 4 is also negative. 2 times negative 10 minus 3 is also negative. So our first one is negative times negative times negative. And that turns out to be, finally, a negative number. Is a negative number greater than 0? That's going to be false. So our first conclusion is false. Next up, 0. 0 is a nice easy one. 0 minus 4, that's negative. 0 plus 4, that's positive. 2 times 0 is 0, minus 3 is negative. So a negative times a positive is negative, and that negative times the last negative will become positive. Are positive numbers greater than 0? Yes, they are. True. So we'll color in that part of our number line. Next up is 2. 2 minus 4 is negative. 2 plus 4 is positive. 2 times 2 is 4, minus 3 is a positive 1. So we've got a negative times a positive, that's negative, times another positive keeps us negative. Are negative numbers greater than 0? No. False. Last up, 10. 10 minus 4 is positive. 10 plus 4 is also positive. 2 times 10 is 20, minus 3 is positive 17. Positive times positive times positive is positive. I'm absolutely positive of that. And are positive numbers greater than 0? Yes, they are. True. So, let's see. Number line. We've got negative 4 as a key number. We've got 1.5 as a key number. And we've got positive 4. The true part was between negative 4 and 3/2. So I'm going to put some parenthesis there because our inequality was strictly greater than, no or equal to. So that's a true component. And then from 4 to infinity. So I'm going to put a parenthesis at 4 and my arrow heading off toward infinity. Now let's see if we can sort of figure out what the two-dimensional graph might look like. We've got a positive 2x cubed. So if we think about end behavior, odd exponent and it's positive is going to be up to the right and down to the left. And then we've got our x-intercepts. So here I am going down to the left. I work my way up. I've got an x-intercept and I'm up above. So here we're positive until we cross the x-axis again. And then we're underneath and then we cross again at 4 and we're off to infinity. Notice where this graph is above the x-axis, we colored in that part as our solution. Here we are above the x-axis, we colored in that part of our one-dimensional number line graph. Where the graph went under the x-axis was a false part. Here we are under the x-axis, we did not color in that part of the graph. Okay, I think one for you to try, and that is the end of this video. Just keep your eye on WebAssign for the assignment. So pause the video and try this one and see if you get it. All right, step 1. Let's get everything on the left. We got a minus 12x. We're going to bring over the 4 where it will be a positive 4 greater than 0. Oop, that was supposed to be a cube there. Factor out an x squared. X squared, and then you've got a 3x minus 1. And here if we factor out a negative 4, that will switch to a positive 3x and then a minus 1 greater than 0. So we're going to have an x squared minus 4, and x squared minus 4 is going to be an x plus 2 and an x minus 2. And then we have our 3x minus 1. Now, if we set each of those equal to 0, we'll get our key numbers. And I guess I can sort of do my number line down here, squeeze it in. So the first one, if we set this one equal to 0, we get x is negative 2. Set the one in the middle equal to 0, and you get x is positive 2. And for this one, we would add 1, divide by 3. That's positive 1/3. 1/3. So intervals, we start all the way on the left at negative infinity, and we'll go to we hit negative 2. And then that interval will begin next at negative 2 and go to 1/3. And then finally, we'll go from 1/3 to infinity. And we can use our nice and reliable test values. Negative 10 is always nice, 0 in the middle. 10 is going to work there, and we're going to figure out three signs. If I plug in a negative 10 for these, all three are going to be negative. Negative 8, negative 12, and negative 31. So that's a negative times a negative, which is positive, times another negative is negative. Are negative numbers less than 0? False. Plug in a 0. 0 plus 2 is positive. 0 minus 2 is negative. 3 times 0 is 0. Minus 1 is negative. So these two negatives would multiply to a positive, and then multiply the other positive. We're still positive. Are positive numbers greater than 0? Yes, true. Last up is 10. 10 plus 2 is positive. 10 minus 2 is positive. 3 times 10 is 30. Minus 1 is positive. All positives multiply to a positive. Ooh. There we go. Oh, I see what I did. I don't have an interval from 1/3 to positive 2. So this last one, if I make this, what would that be? 2. This interval's 2 to infinity, and we can use 10. So that is going to be positive, but we got to squeeze another interval in there. I am so sorry. We need an interval from 1/3 to positive 2. Yeah, right from here, from 1/3 to positive 2, we did not account for that one. Okay, and I guess a good number between 1/3 and positive 2 would be a positive 1. So let's put 1 in there. 1 plus 2 is positive. 1 minus 2 is negative. 3 times 1 is 3, minus 1 is positive. So positive times positive is positive. We hit it with another negative, and that is negative, and therefore false. And that one was true. Okay, so, well, I'm going to redo my number line up top. It's getting a little crowded there at the bottom. First interval was false, so we would go to negative 2, and that part is not going to be colored in. But negative 2 to 1/3 is true, so that's going to be colored in. 1/3 to 2 is false, so that will not be colored in. And then the last one, 2 to infinity, was true, so we head off there, that's colored in. Okay, that's the last problem. Again, look for the assignment on WebAssign. And the next video will cover the rational inequalities.